So now let's revisit back this particular problem. So we have started our reference point, we choose at 25 degrees Celsius, 1 atm solid. And then we know that from the table B1, we have actually figured out what will be the properties of phenol, such as the melting point temperature as well as the boiling point temperature. So in order for us to draw the hypothetical process path, is actually we should think about the changes of this solid phenol that it has to undergo through in order for it to become vapor at 3 atm and 300 degrees Celsius. So what happened is that there is a change of the there is a what we call as change of temperature. So you can see that there is a change of temperature from 25 degrees Celsius to become 42.5 degrees Celsius. So there is one change. So this is what we label as delta H1, and it is at 1 atm and it is at solid, which is at constant pressure and constant phase. There is no state of aggregation, there's no phase change. And then the next point that it has to undergo through is actually there is a change of phase from because this is a melting point of phenol. So at constant temperature and constant pressure, there is a change of phase from solid. Now we become liquid. So this is delta H2 that we need to calculate. Okay. And we need to also find the values. For example, like when there is a change of temperature at constant pressure as well as constant state. Now this is where actually 42.5 degrees Celsius, okay, from the initial point it becomes liquid until it becomes the liquid at 181.4, which is before it turns into vapor. So this is another state, okay, another change which is now we label as delta H3. And if we look at now, because there is a change of liquid to become vapor at constant temperature and pressure, so there is a change again. This is where actually we label as delta H4. And right now, there are also another change of temperature, which is 181.4 to become 300 degrees Celsius at 1 atm and vapor. So this is delta H5. And finally, there is a change of pressure, which is actually from 300 degrees Celsius, 1 atm vapor to 300 degrees Celsius, 3 atm vapor. So it becomes delta H6. So in order for us to calculate the delta H total, okay, then we must make sure that everything is added up together. Delta H1 plus delta H2 plus delta H3 plus delta H4 plus delta H5 and plus delta H6. So only then we'll be able to calculate the enthalpy changes in total. Okay. So in order for us to calculate delta H6, which is the change of pressure, there is a formula where actually we can use V delta P. V is means that it is at constant volume, and delta P is the change of pressure. You have to bear in mind that, however, if let's say the change of the temp of the pressure is less than 50 bar, okay, if it less than 50 bar, then basically we can just eliminate the term. We can just actually cancel it out. So we don't have to calculate it. But if let's say it is more than 50 bar, then we have to calculate it because there is the change of pressure is the enthalpy change in terms of changing pressure is quite significant. Otherwise, the value is relatively small if you calculate. You can try to calculate, but the relative value is relatively small. Okay. So in order for us to calculate the hypothetical process path, we need to determine the values for delta H1, delta H3, delta H5, and delta H6. However, for value of delta H2 and delta H4, which you can see from here as being circled here, is actually you can determine from the table. Okay, from the table, which can be obtained from table B1, and then we can solve for the total by adding it up together. So that is actually how we can determine the changes of phenol from solid state to become the gaseous state. So this is where actually we can calculate the heat, the enthalpy change for those state. Okay, from phenol at solid state at 25 degrees Celsius, 180 m to 300 degrees Celsius, 3 bar, and in vapor state. So as such, in order for us to produce to perform the energy balance, there are certain procedures that we have to follow. Okay, and then there are examples that I'm going to share with you how we can perform step-by-step procedure to solve the energy balance. Now let's look at the example, which is material and energy balance on a condenser. You were given acetone, which is at 65 degrees Celsius and 180 m. It is condensed, partially condensed from a stream containing 66.9 mole percent of acetone vapor, and the balance is nitrogen. Okay, so can you imagine that there is acetone coming in, and then there is a condenser. So it is partially being condensed. Some of it, okay, go to acetone vapor. Some of it becoming liquid. Okay, because it's just partially condensed, not 100% condensed. And then there are also some amount of nitrogen inside the stream, and 63.45% of the feed leaves at the bottom stream at 20 degrees Celsius and 580 m. So we know that whenever that we're trying to condense things, the liquid will go at the bottom and the vapor will go to the top. And this stream only consists of liquid acetone, which means that at this particular point, this is acetone, which is in liquid, 100% value. Okay, but at the top here, this is like and then from it's actually you have some amount of acetone which is in vapor, and you have also nitrogen. This is at the top here. This stream only consists of liquid acetone. The top product stream flows out also at 25 degrees Celsius and 580 m. So the condition here, this is 25 degrees Celsius, 580 m, which is similar to up here. Okay, with 9.2 mole percent acetone and 90.8 mole percent of nitrogen. So you have 0.092 of acetone and 0.908 of nitrogen. Okay, so that's the information given. The process operates at steady state. So calculate the required cooling rate. So we wanted to know how much condenser, the cooling rate that is required to be supplied to the condenser, so we can get this particular value. So how do we perform the energy balance for this?